Today we're going to be looking at notes 3-1. We are going to be using graphs and tables to solve systems of equations. So a system of equations is a set of two or more equations containing two or more variables. On the graph of a system of two equations, the solution is the set of points where the graphs intersect. A point is a solution to a system of equations if the x and y values of the point make each equation true. So meaning, look at this system of equation. I've got a point where these two lines intersect. This coordinate for this one would be -2, +1. So this coordinate, -2, +1, should plug into both of these equations of these lines and work out. So, for example, whatever coordinate where these two equations line up, I can take that coordinate, plug the x value in for x, plug the y value in for y, and this will be a true statement. Same for this second equation here. All right, when solving linear systems of equations, graphically, you're finding intersections of lines. For two variable systems, there are three possible types of solutions. So this is what we'll be working with for the next few days. So if I have two lines, it's possible that they intersect at one point, okay, and that one point is the solution. It's also possible that two lines can be parallel forever. They're never going to touch. So if they never touch, they never intersect, then there's no solution. Last but not least, if two lines are the same exact line, they lie on top of each other and touch forever. So that is said to be infinitely many solutions. They touch forever, so it's infinitely many solutions. Another thing that these solutions are classified as, some more fancy math words here, we say if a system has either at least one solution, we call this consistent. So consistent means there's at least one or more solutions. So both of these types would be consistent. And this type, because there's no solution, is said to be inconsistent because there's no solution. So you see here we've got two possibilities that are consistent. So how do you classify the two? Consistent, if there's one solution, it's said to be independent, consistent and independent. And if it's consistent with infinitely many solutions, it's consistent and dependent. All right. So let's use a graph to solve each of the following systems and then check our answer. So this line here is already in y equals mx plus b, so I can plot it. -2 is my y-intercept, and 1/2 is my slope, so that means I go up 1, right 2, up 1, right 2, because it's positive. That's why I'm going up and right. I could also go down and left. Alrighty, so there's my line. Okay, I'll draw the best line through it that I can. Great. Okay, this one here is not, however, in y equals mx plus b, so I need to move over that x to the other side, so that would make it y equals -x plus 4. When I move the x over to the other side, it becomes negative. So 4 is my 4 is my y-intercept. -1 is my slope, so that means down 1, right 1, down 1, right 1. And there it is, our point of intersection. Okay, I don't really even need to go any further because it's right there. So what is that coordinate? That coordinate is 1, 2, 3, 4, 0. So the coordinate 4, 0 is my solution, and it says to check my answer. Well, how could I check it? I need to plug that point into each equation and see if it works. So if I plug in 0 for y into this first equation here, 0 equals 1/2, x is 4, minus 2, this should be a true statement. Okay, so 0 equals 1/2 times 4 is 2. So 2 minus 2, is it 0? 0 equals 0, definitely. Okay, so now plugging into the next equation, y equals, so 0 equals negative x, which would be negative 4 plus 4. Okay, 0 equals 0, definitely a true statement too. So we have just checked that we have graphed correctly and our point has come out correctly. All right, let's move on to the next one. So here on this one, we've got quite a bit more maneuvering to do on this equation here. So let's take it down. I know that that's going to be 2y equals 4x. First thing I'm doing is I'm moving that 8 over, okay? So I know that that is going to be my y-intercept. I need to move it over, so it becomes negative 8. Now I know I need to divide everything by 2 to get rid of that 2y, so this would be y equals 2x minus 4, okay, when I divide everything by 2. So now I can plot 1, 2, 3, 4 is my y-intercept, positive 2 is my slope, so up 2, right 1, up 2, right 1. The first line you kind of have to graph the whole thing because you really don't know where your intersection is going to be. The second line, not so much. So, all right, looking at this one, oh yay, it's in y equals mx plus b form. Wait a minute, y equals 2x minus 4. That's the same exact line. Okay, so those are the same exact line. Really no reason for me to draw it all over again, but I just want you to see. Same exact line, so they touch in infinitely many places. So my solution is infinitely many solutions. Okay, I can pick any of these points here, and any one of these points, if I plug it back into any equation, will work out for both. Okay, so your answer for this would be infinitely many solutions. If you want to put in parentheses, same line, that would be great. Okay, so now that we know how to graph and find a solution, let's use a table. Okay, so sometimes a table is more easy or sometimes it's just as easy. So let's go ahead and let's get both of these. Even when we do a table, we need to put it in y equals mx plus b. So for this first equation here, I'm going to change that, come down here, y equals, when I move that 5x over, it's going to be negative 5x plus 11. Okay, so that's my first equation. My second equation here is negative y equals, all I'm doing first is moving over the x, so negative x plus 1. Okay, I know that I can't have that negative, so this will become y equals x minus 1. Okay, so here are my two y equals equations. All right, and now for a table. So this is a tricky thing, kind of. Okay, an x and y table. I'm going to make it long because I have no clue where my solution is going to be. The easiest thing to do is to start with 0. Okay, so if I plug in 0 for x into the first equation, and actually this is going to have two y's because we have two equations. So if I plug in 0 here, 0 times negative 5 is 0, plus 11 is 11. So for the first equation, my answer is 11. For the second equation, if I plug in 0 here, 0 minus 1 is negative 1. Okay, let's move on. Those definitely are not the same coordinate, so that's not where they intersect. What if I plug in 1? Let's see if these numbers are getting closer together. If I plug in 1 here, negative 5 times 1 is negative 5, plus 11 would be 6. Okay, if I plug in 1 here, 1 minus 1 is 0. Okay, are those numbers getting closer together? Yes, they are. So let's keep going. Okay, in that same direction. If I plug in 2 here, negative 5 times 2 is negative 10, plus 11 is 1. If I plug in 2 here, 2 minus 1 is 1. Well, looky there. So when I plug in the x value of 2 for both of these equations, the y value that I get out for both is 1. That means they share that point. They share that point in common. They both have the point 2, 1. So these two lines must intersect at the point 2, 1. That is your final solution. That's when they're exactly the same. Okay, sometimes you get real lucky that it happens real soon. So let's look at this one next. So on this one, again, got to put them in y equals form. So this would be y equals negative x plus 6. When I move over the x, this one here would be negative y equals negative x plus 4. Okay, get rid of the negative, so y equals x minus 4. All right, there's my two equations that I'm going to be plugging into. And let's see if we don't have to go too far on this one either. So, let's see, x, y, and y. Again, you always want to start with 0 because it's such an easy number to compute. If I plug in 0 to the first one, negative 0 is 0, plus 6 is 6. 0 for this one, I'd get negative 4. Okay, if I plug in 1 to this one, negative 1 plus 6, that would be 5 when I plug in 1. When I plug in 1 to this one, 1 minus 4 is negative 3. Okay, these numbers are already getting close together. Yay, these numbers here are getting closer together. So 2. If I plug in 2 here, negative 2 plus 6, that will give me 4. If I plug in 2 here, 2 minus 4 is negative 2. Okay, these numbers are getting smaller. These numbers are getting larger. They're getting even closer. So 3. Plug in 3 here. Negative 3 plus 6 would be 3. 3 here. 3 minus 4 would be negative 1. Plug in 4. 4 here would be negative 4 plus 6, which would be 2. Plug in 4 here. This would be 0. If I plug in 5 here, negative 5 plus 6, that would give me 1. Plug in 5 here, 5 minus 4, that would give me 1. Yay! So there we go. They match up at 5. So my coordinate of intersection for these two lines would be the point 5, comma 1. Okay, so notice I left room to go in the negative direction. If I had noticed here that these numbers were getting further away from each other as I was going, I would have gone back into the negative direction. So, of course, you're always going to hope that doesn't happen, but leave some room for yourself just in case.